This is Math 432 Applied Combinatorics. I'm Professor Asaph, and we're going to be talking about sieve methods. We'll start with an example. Adelie has 3 red dinosaurs and 3 Tyrannosauruses. How many dinosaurs does Adelie have in total? So this is a basic counting problem that you can give to a small child. You can say, okay, well, we know she has 3 Tyrannosaurus Rexes. Okay, here are the T-Rexes. And she's got 3 red dinosaurs. So here's the red dinosaurs. Stand those up. So we could just count how many dinosaurs Adelie has. So it looks to me like she has 6. But actually that's not the case. Because Adelie could have these 3 dinosaurs. So she could just have 3. So what's the answer to the question? Well, you don't know. She could have 3, or she could have 4, or she could have 5, or she could have 6. If she doesn't have any red Tyrannosaurus Rexes, then she's got 6 dinosaurs because these 2 sets, the red dinosaurs and the T-Rexes, are disjoint. On the other hand, at the other extreme, if all of her dinosaurs are red T-Rexes, then she's only got 3. But of course, we could combine this. She could end up with here having 5 dinosaurs, right? There are 3 red and there are 3 T-Rexes because one's in the middle. And what this is a great example of inclusion exclusion. So you know this, you've seen it before. It is the idea that if you want to count the number of objects in the set of red dinosaurs, union the set of T-Rexes, what you have to do is you have to count all the red dinosaurs and you have to count all the T-Rexes. And you have to remember that you have overcounted the red T-Rexes. So if this was Adelie's setup, then she would count 3 for the red dinosaurs, plus 3 for the T-Rexes, minus 1 for the red T-Rex, and you would see that she indeed has 5 Tyrannosaurus Rex, or 5 dinosaurs total. This is the basic property that's incredibly powerful, and it's called inclusion exclusion. And here is the general statement of the theorem. If I take n sets, A1 up to AN. They need to be finite sets, of course, because we're going to be counting. Then, if I want to count their union, I take an alternating sum of the intersections. It's important that this is a lot of notation here, but it really is just this statement again. Okay, so the notation here is just saying I sum over all possible combinations of exactly k subsets and intersect them. And I count it with multiplicity minus 1 to the k minus 1. Here you see 2 sets, I get minus 1 to the 1. Okay, let's think about why this is true. We want to give a proof of this statement, of course. So how does this work? Well, it comes down to dinosaur counting again, right? I want to make sure that I count everything exactly once. So here's the proof. What I want to do is I want to think about an element. So I want to suppose that x is in A1 union all the way up to AN. So think about that element x. How many times does x get counted in this summation? Okay, well, we need to know more about x. So let's suppose that x is in AI1, sorry, not union, and AI2, and all the way up to AIK for some K. So these are the sets that A belongs to. Okay, A is red and it's a T-Rex and it's super tall. I don't know what all these are, but they're all the properties that it could have, okay? And I want to suppose that X is not an element of AJ for any J that's not in this list. So if J is not I1 up to IK, it's not there. So X is in exactly these sets. It has exactly these properties. That's often how we think of these A's, as properties, okay? Now let's look at this formula and let's figure out how many times we count X. And it's going to be counted either positively or negatively, okay? So let's think about the positives. So X is counted plus 1 in how many ways? Well, every time I take any of these K sets, right, and K minus 1 is even, I'm going to get it. So that's going to be in K choose 1. If any one of these sets, it'll be positive. Also, when you take 3, and in general, if I take any 2i minus 1. Okay, so every time I take an odd number of these, There are k of them total. Every time I take an odd number of them, any combination of an odd number of them, I'm going to count x in this formula with a positive sign. Okay? How often is x counted with a negative sign? So x is counted -1 times. How many times does that happen? Well, again, look at this formula. It's going to be all the even times, right? So if I take 2 of those sets, it's going to show up as a pairwise intersection. That'll give me a negative sign. And of course, if I take 4 of those sets, and on and on and on, up until k choose 2i of those sets, and on and on. Okay, so this is how many times I count x, right? It just matters when I count it in any of these intersections. Any subset of these, it'll still be in their intersection. So let's continue the proof on over here. What do we know? Well, what does that tell us? Well, that tells us in total, how many times have we counted x? We've counted x, the sum from I equals 1 to k of what? -1 to the I minus 1, k choose I. This is how many times we've counted x. So how many times is that? Well, by the binomial theorem, remember that we know that if we take the sum from I equals 0 to k, different indexing set, of -1 to the I, k choose I, we know what this is. It's 0. That's plugging in 1 for y, or 1 for y and -1 for x. We've done that before. So what's this? Well, it's just one more. So we've counted x exactly once. Of course, you can also prove this using the property that we had before on the 2-set case and doing mathematical induction. So if you're careful with how you do your induction, you can prove this by induction. But this is maybe an easier way to see what's really going on behind this counting. And next, we're going to look at some exciting applications of this idea in order to count something that it seems a priori incredibly difficult to count.